Okay, let's be real. We are absolutely drowning in data these days. But how do you find the real story? The actual signal that's hiding in all that noise? Well, today we're going to dive into two incredibly powerful tools, PCA and SVD, that help us do just that. Let's get into it. So it all starts with this one fundamental question. When you're staring at a data set with maybe thousands of different features, how in the world do you figure out which ones actually matter? I mean, think about it. If a feature's value is the same for every single data point, it's totally useless, right? It's not telling you anything new. And that right there leads us to our first huge idea. The most important, the most significant features are the ones that change the most. They're the ones with all the action. And in the world of data science, we have a specific name for all this action. That name is variance. It's really just a way to mathematically measure how spread out our data is. It lets us put a solid number on that action we were just talking about. So a high variance means a feature is changing a lot, and that is a huge clue that it's probably hiding some really important information. Now, what's so cool about this is we can capture all of this information in one place. We can calculate the variance for every single feature. Those are the numbers you see running down the diagonal of this matrix. But we can also measure how features change together. Like does one tend to go up when the other goes up? That relationship is what we call covariance. And we can pack all of that, the individual action and the teamwork, into this one powerful summary, the covariance matrix. So this whole thing really just boils down to one simple but incredibly powerful idea that's going to guide us for the rest of this journey. High variance equals high significance. We are on a hunt for variance because that's where the real story is hiding. And our first tool for this hunt is something called principal component analysis, or PCA for short. And it is built entirely on this one principle of finding the variance. So what even is PCA? Well, at its heart, it's a clever algorithm that transforms our data by finding a much better way to look at it. Just imagine you're trying to film a really busy intersection, but your camera's at a terrible angle where a building is blocking most of the view. PCA is like moving that camera to the perfect spot, the perfect angle where you can see all the important action happening clearly along one single line of sight. And this right here, this visual, this is the big aha moment for PCA. On the left, you've got our original data, just kind of spread out in two directions. What PCA does is it finds the one direction where the data is most spread out. That's our new camera angle, and it rotates the entire system. Now look at the right. Almost all the important information, all of that precious variance, is perfectly lined up along that new horizontal axis. And that axis is our first principal component. The real magic here is that these new features, these principal components, are totally independent of each other. The source notes call this decorrelating the data. What that really means is that all those messy, overlapping relationships from before are just gone. We're left with this clean, simple picture, where each new axis tells its own unique part of the story with zero interference from the others. So how does PCA actually find these magical new directions? Well, under the hood, it's solving something called an eigenvalue problem. Now, don't get hung up on the math here. All you really need to know is that this process finds two critical things for us. First, the exact directions of our new axes. Those are the principal components. And second, it gives us a score for each axis that tells us just how much variance, how much importance is captured along that new direction. Okay, so PCA is fantastic. It's a game changer. But what if I told you that PCA is just one little piece of a much bigger and honestly a much more beautiful puzzle? It turns out it's just a special case of a more fundamental idea in math, one that explains how all data transformations really work. And that is the Singular Value Decomposition, or SVD. This brings up a really fascinating question, right? We've seen how PCA rotates data to find variance. But is there maybe a more fundamental, a more geometric way to think about what any data transformation is really doing? And the answer is yes, absolutely. And it is just beautiful. Get this, it turns out that any matrix, which represents any linear transformation you can do to data, fundamentally does only one thing. It transforms a simple circle of data points into an ellipse. That's it. All that complexity, all that math, it all just boils down to this one simple geometric truth.
So the huge insight here is that any complex data transformation isn't some crazy black box of math magic. Nope, it can always be broken down into a simple series of intuitive geometric actions. It's all just geometry.
And SVD tells us exactly what those actions are, and there are only 3 of them. First, it does an initial rotation. Then, it stretches or maybe squishes the data along the new axes. And finally, it does a second rotation in that new space. That is all any matrix ever does. It's just rotate, stretch, rotate. And this is how we write that out mathematically. Our data matrix A is equal to U, which is the second rotation, times sigma, the stretch, times V transpose, which is that first rotation. This right here is the singular value decomposition. It's the fundamental recipe for any linear transformation. So we have this beautiful, super general theory of SVD, but what in the world does this have to do with our original problem? Well, let's bring it all together and reveal the ultimate connection between SVD and PCA. Okay, so let's remember our goal with PCA, right? We needed to solve that tricky eigenvalue problem just to find the principal components from the covariance matrix. And that can be super expensive to compute, especially if you have a massive data set. So the question is, can SVD give us a shortcut? The answer is a spectacular yes. This is the elegant connection we've been building up to. So remember how PCA had to build that giant covariance matrix and then solve a complicated problem to find the principal components? Well, SVD just takes our original data and breaks it down into its 3 geometric actions. And here's the incredible part. That V matrix from SVD, the one that does the very first rotation, that matrix is our set of principal components. SVD just hands them to us directly, without any of the extra work. And this isn't just some cool theoretical trick either. This has huge practical benefits. As the source notes point out, instead of building that giant covariance matrix and then finding its eigenvectors, we can just run SVD on our original data. It's often way more stable and efficient, which is absolutely crucial for the massive high-dimensional data sets we're dealing with today. So let's just recap the big takeaway here. PCA is looking for significance by finding the directions of highest variance, and SVD gives us this fundamental truth about data. Any transformation can be broken down into a simple recipe of rotation, stretching, and another rotation. And by using SVD, we get the answer to PCA's question directly, elegantly, and way more efficiently. Which really leaves us with one final thought. We've seen how these tools can slice through incredible complexity to find the absolute core components of our data. So the real question is, if we can apply this kind of lens to any data set out there, in science, in finance, even in art, what hidden stories, what fundamental truths are just sitting there waiting for us to finally uncover them?